In exercise 6.6, they're giving you different values for delta G and for K, and they're asking you whether that reaction, in each of those reactions, the reactants or products are favored. So you'll notice that there's a lot of overlap between delta G and K. If delta G is positive, well, let's say if delta G is negative, then that favors the reactants. Favors the products. That means the reaction is going to happen and you'll make the products. If delta G is positive, then it favors the reactants. The reaction is unlikely to happen, and so you won't get the products. You'll mostly have the reactants. So that's delta G. For K was if K was, remember, K is products over reactants, conceptually, products over reactants, and so you have 1 as a sort of, where you have equal amounts of products and reactants. But if you have a number bigger than 1, then it favors products. If K is bigger than 1, then that means you have a bigger number on top of the fraction, and you have more products. And if it's smaller than 1, and if K is smaller than 1, then you have more reactants because the denominator is larger. So you can see that a K bigger than 1 is like having a delta G that's negative, and a K smaller than 1 is like having a delta G that's positive. Both of those are really giving you the same information about a reaction. And you would have noticed this in general chemistry too. You had different chapters. You had a chapter on thermodynamics where you talked about delta G. You had a chapter on equilibrium where you talked about K. You had a chapter on electrochemistry where you talked about E of the cell. And then after you learned about each of those individually, you learned equations that related them to each other. For example, delta G equals negative RT times the natural log of K. So you can see that delta G and K are interchangeable, which is exactly what we're seeing in this table here. And so all of those equations are really kind of like the story of all of these variables are really kind of like the story of the blind man and the elephant. In the story of the blind man and the elephant, 3 blind men were placed around an elephant, one in the front, one on the side, one in the back, and they were asked what was in front of them. And the guy in front reaches out and he grabs the trunk and he's like, well, I have no idea what this is, but it's got a couple holes on the end and it's kind of long. Excuse me. The guy on the side reaches out and he feels the side of the elephant and he's like, well, I have no idea what this is, but the first guy is definitely wrong. This is clearly a broad, wide thing that's kind of flat. And the blind guy in the back reaches out and he grabs the tail and he's like, well, I have no idea what this is, but the first 2 people are clearly mistaken. This is thin and it's got hair at the end. But all of them had the same thing in front of them. They were all describing an elephant and looking at it from a different perspective, from a different angle. And so likewise, in general chemistry 2, you were studying each of those chapters. We're all trying to understand what happens in the world. They were all looking at the same world, the same elephant. But from a historical perspective, some people thought of the world and framed their questions in terms of probability, and others framed their questions in terms of how many products and reactants they had in a watery solution. But they ended up with the same description of the world, descriptions that are interchangeable with those equations that relate one variable to the other. And so you end up with these different variables that all describe the same thing, these different perspectives used for describing the same world, perspectives that were developed differently for historical reasons. So you can see that you can use these values, you can use either delta G or K to predict whether a reaction favors the products or the reactants. Incidentally, if K is 1, that's like having a delta G of 0. You could have those values, they just mean that you're neither creating more products nor more reactants, you have about an even amount of both. So we can bring that to the analysis in exercise 6.6. They say, use the information that they give you to determine whether the reaction favors reactants or products. Well, here we see that delta G is positive. That means the reaction is unlikely to happen, and so it favors reactants. If the reaction is unlikely, then the reactants are not going to change into products. In B, we have a K that's less than 1. That means you have a larger number in the denominator than in the numerator. Right? Now this would be like 1/2. You have more reactants. A K less than 1 favors reactants. For C, they say a reaction carried out at 298 Kelvin, for which delta A, and then they give you values of delta H and delta S. And so with this, you just want to plug those values into our old equation, delta G equals delta H minus T delta S, and we can see quantitatively whether that reaction is likely to happen. So in the enthalpy here, the energy is not arranged in a very favorable way. We're looking at, and notice the units are really the place where most people make a mistake. I'm going to plug in the kilojoules for delta H, so that's positive 33 kilojoules per mole. We know the temperature is 298 Kelvin, but then when we plug in the value for delta S, we have to convert this to kilojoules. So we have 150 joules times, we know that in every 1,000 joules there's 1 kilojoule, and so that the joules cancel, we're left with kilojoules, and that gives us 0.15 kilojoules. Kilojoules per mole Kelvin. And so now we plugged the numbers in with all the correct units, and we can see in this case the entropy is increasing, so that would make the reaction want to happen. So we have this making the reaction want to happen. We have the molecules. The delta S is positive, so the molecules are changing in a favorable way. The delta H is positive, so the molecules are changing in an unfavorable way. And if you plug all of those numbers in a calculator, you'll get 298 times 0.15. I'm getting around 44.7. 44.7 there. And we have 33 on the other side, so we have 33 minus 44.7. So 33 minus 44.7, and that's giving me negative 11.7 kilojoules per mole Kelvin for delta G. So the number and the units don't really matter. What really matters here is, now that at the end, when you plug them in, you have to make sure the units match, of course. But at the end, what matters here is that delta G is negative. And what that negative sign means is that this reaction is likely to happen. This reaction will favor the products. Because delta G is negative, the reaction is likely to happen, and so it'll favor the products. And notice the number here tells you quantitatively exactly how likely it is to happen. The more negative, the larger the negative number, the more likely the reaction is to happen. D and E are bringing us back to types of problems that we did earlier. We're going to think qualitatively about this equation. We're thinking, is a reaction likely to happen? It depends. Is the energy going to change in a way that's more likely? And are the molecules going to change in a way that's more likely, that makes their arrangement more likely? Well, they tell us that the reaction is exothermic. That means that delta H is negative, and so that's favorable. The heat is spreading out. And they tell us that delta S is positive. So the entropy is increasing. That means the molecules are spreading out. Either you have more molecules that can go off in different directions, or you have a ring becoming a straight chain that can rotate in different directions. So remember, you subtract that term. So if delta S is positive, when you subtract it, it's overall negative. And so delta G will always be negative. That reaction is always spontaneous. That reaction always favors the products. If we take that same equation, is a reaction likely to happen? Well, it depends. Is the heat changing in a way that spreads out? And are the molecules changing in a way that spreads out? We can look at what the information they give us. They give us an endothermic reaction. That means heat that is spread out is coming together. That's unlikely. It's a positive sign for the delta H. And they tell us that the molecules that are spread out are coming together to give us a negative value for delta S. And remember, you're always subtracting that term. Subtract a negative, that's a positive. So we have positives for both of our terms. So the delta G, which is the sum of those, will always be positive for this. That means the reaction is unlikely to happen, and so it will favor, the equilibrium will favor the reactants. So you can see how you can use either the delta G values or the K values to figure out whether a reaction favors products or reactants.